In this video, we're going to look at homogeneous linear equations with constant coefficients. We're going to show that the general solution, x sub h, of the homogeneous linear constant coefficient equation can always be found. We're going to find and use a characteristic polynomial to determine the types of solutions, and we're going to find the solution sets based on the discriminant of the characteristic polynomial. So we know from our last section that second order homogeneous ordinary differential equations will have the form of a x double prime of t plus bx prime of t plus cxt is equal to 0. And it's always a reasonable guess to say the solution is x of t is equal to e raised to the rt. If x sub t equals e raised to the rt, then its first derivative is going to be re raised to the rt, and its second derivative is going to be r squared, e raised to the rt. Then our second order homogeneous ODE becomes ar squared e to the rt plus br e to the rt plus c e to the rt is equal to 0. Factoring out e raised to the rt, I'm going to get ar squared plus br plus c, which we now have e raised to the rt some p of r, where p is the characteristic polynomial. It is ar squared plus br plus c, and we can solve this using the quadratic equation, where r will equal negative b plus or minus the square root of b squared minus 4ac all over 2a. The thing that we really want to focus in on then is the discriminant, because it's going to give us all kinds of information. Discriminant, of course, just like we learned in Pre-Calculus 1, is the value underneath the square root. If my discriminant is greater than 0, we're going to have two real solutions. X sub 1 of t is going to equal e raised to the r sub 1 of t, and x sub 2 is equal to e raised r sub 2 of t. And we know that x is equal to some constant x sub 1 plus some constant x sub 2. It's going to be the general solution. If k is equal to 0, then there's only one real solution, and we call it r bar. And it would be x sub 1 of t is equal to e raised to the rt. And it turns out that x sub 2 of t is equal to t e to the rt will also be a solution. This will form our general solution. And the last and final case is when my discriminant is less than 0. If that happens, there are two solutions, and they're both going to be complex. Z being the representation of the complex, z sub 1 of t is equal to e raised to the alpha plus beta I of t, and z sub 2 is equal to z sub 2 of t is equal to e raised to the alpha minus beta I of t, where alpha plus beta I, alpha plus and minus beta I, are complex conjugates. To find the real solutions, we are going to use Euler's formula, where e raised to the theta I is equal to the cosine theta plus I sine theta. So this goes back to our pre-calculus 2, when we were learning complex numbers in using polar form. So then z sub 1 of t becomes e raised to the alpha t cosine beta plus I sine beta t, and z sub 2 will be the exact same thing with the exception of I'm going to have a minus sign between them. Since the linear combinations are the solution, then x sub 1 of t is equal to z1 plus z2 over 2, which using e to the alpha t cosine beta t, and x sub 2 of t will end up becoming e the alpha t sine beta t, and this will form the general solution. Here is a nice summary of what we expect to see as solutions based on our discriminant. So the first thing we're going to want to do, of course, is to find our characteristic polynomial, determine what our discriminant is, and then from there we'll be able to figure out what our general solution is. So the first thing we're going to do is determine what my characteristic polynomial is for this example. Pretty much the characteristic polynomial, provided of course that I don't see any variable, my independent variable here, so I don't see if my independent variable is say x, I don't see x there. If my independent variable is t, I don't see t there. My characteristic polynomial is going to be all these coefficients on the the y double prime, the y prime, and the y. So my characteristic polynomial would be r squared multiplied by 1 plus 11r plus 24. Now it's just a matter of factoring, and this one actually factors quite nicely. This factors into r plus 3 and r plus 8 is equal to 0. Because this factored over the reals, I didn't take the time to find the discriminant, but I absolutely could. My discriminant is b squared minus 4ac, so I'd have 11 squared minus 4 multiplied by 2 multiplied by 24, and this is clearly going to be bigger than 0. So once I've found what my r's are, my r is going to be either -3 or my r is going to be -8. I go up here and I say, oh look, my x sub t must be equal to c sub 1 e raised to the, I'm going to use -8 first because it's the smaller number for no other reason, plus c sub 2 e raised to the -3t. Now I'm going to use my initial conditions to see if I can figure out what my c sub 1 is and my c sub 2 is. Using my first initial condition, I have 0 is equal to c sub 1 e to the 0 plus c sub 2 e to the 0. So I have 0 is equal to c sub 1 plus c sub 2. This tells me that c sub 1 is equal to -c sub 2. Now I'm going to use my second initial condition. So I'm going to take the derivative of my x sub t, so x sub t, or actually I should have y of t, excuse me. These are y of t, because my variable was y, so I should, stay consistent. Y of t, this is going to be -8 c sub 1 e raised to the -8t minus 3 c sub 2 e raised to the -3t, so that's just taking the derivative. Now I'm going to use that second initial condition and say, hey, -7 is equal to -8 c sub 1 e to the 0 minus 3 c sub 2 e to the 0. So my second equation is -7 is equal to -8 c sub 1 minus 3 c sub 2. But I have this information I can plug in there as a substitution. So what I end up with is -7 minus, or equals to, -8 multiplied by. If I say c sub 1 is equal to -c sub 2, so this is going to be -c sub 2 as my replacement, minus 3c sub 2. So -7 is equal to 8c sub 1 minus 3c sub 2. -7 is equal to 5c sub 1, c sub 2, excuse me, c sub 2. And so my c sub 2 is going to give me the c sub 2 will give me -7/5. That means c sub 1 must be the opposite, which is +7/5. So my solution then of y of t is going to be equal to 7/5 e raised to the -8t minus 7/5 e raised to the -3t. And that is my solution for that homogeneous system with those given initial conditions. Let's take a look at my second example here. My characteristic polynomial we know is going to be 4r squared minus 4r is equal to 0. And you're thinking, wait a minute, shouldn't I have a constant? We don't need one. We factor out an r, leaving me 4r minus 5 is equal to 0. So I get r is equal to 0, and I get r is equal to 5 over 4. And from this, I'm going to get my y of t is equal to c sub 1 e raised to the 0t plus c sub 2 e raised to the 5/4 of t. So in other words, y of t is equal to c sub 1 plus c sub 2 e raised to the 5/4 of t. Now I'm going to use my first initial value right here. I'm going to say, okay, well, I have -2 would be equal to c sub 1 plus, 0 would be equal to, I was just so excited I was going to put 0 in, but I was putting it in the wrong place. So 0 is equal to c sub 1 plus c sub 2 e raised to the 5/4 multiplied by that -2. So 0 is equal to c sub 1 plus c sub 2 e raised to the 5/2. So that is my first equation. Now my second equation is I'm going to need to take the derivative. So I'm going to take the derivative, and so I have y prime of t is equal to, well, the derivative of a constant is 0. Then I'm going to get 5/4 c sub 2 e raised to the 5/4 of t. Using this second initial condition, I have 7 is equal to 5/4 c sub 2 e raised to the 5/4, I don't know why I wrote 7, 5/4, and then I have -2 as my replacement. Multiplying both sides by the reciprocal of 5/4, and then multiplying both sides by e raised to the positive 5/2, I'm going to get c sub 2 is going to equal to 28 over 5 e raised to the 5/2. If that's my c sub 1, or c sub 2, I'm going to plug that back into here to find my c sub 1. I end up getting a c sub 1 is equal to -28 over 5. So my final equation then is y of t is equal to, I end up with -28 over 5 plus 28 over 5 e raised to the 5/2 multiplied by e raised to the 5t over 4, and I can, of course, combine the last two and rewrite this as y of t is equal to -28/5 plus 28/5 e raised to the, let me see if I've got all my, I've got 5/2 plus 5t over 2. And I guess I could write this if I really wanted to. I could write this exponent as 10 plus 5t all over 4. And this should be a 4 right there, if I wanted to. I'm not going to. Let's take a look at our next example here. And for my next example, my characteristic polynomial is going to be r squared minus 4r plus 4 is equal to 0. This factors into r minus 2, the quantity squared is equal to 0. So I have a repeating, and if I have a repeating, I have r1 and r2 is going to be equal to 2. So we know when this happens, I have y of t is going to be equal to c sub 1e raised to the 2t, and then plus, this always ends up having an extra t, c sub 2t e raised to the 2t. So if you have a repeating, you'll have a general solution that looks something like this, of course, based on your r. Now I'm going to use the first initial condition to find my c sub 1 and my c sub 2. And so I have 12 is equal to c sub 1 e to the 0 plus c sub 2 t e to the 0. Oh, but wait, t is 0. So that's going to be 0 as well. And so I have my first c sub 1 is equal to 12. That's really nice, isn't it? I mean, that's really nice. Now I'm going to take my derivative here. So I'm going to come up here and I'm going to find my derivative. So y prime of t is going to give me 2 c sub 1 e to the 2t plus, oh, look, this is where it's not so nice. We have to do the product rule. But it's not that bad, right? Derivative of a product rule. So I have c sub 2, the derivative of t, which is 1, e raised to the 2t, plus c sub 2, t, e raised to the 2t multiplied by 2. Now my initial condition on this one is that it's equal to -3. So -3 is equal to 2 c sub 1 e raised to the 0 plus c sub 2 e raised to the 0 plus c sub 2 multiplied by 0 e raised to the 0 times 2. Now, we happen to know what c sub 1 is. We found that without doing any work. That was 12. So I have -3 is equal to 2 multiplied by 12 plus c sub 2. So that tells me that my -27 is c sub 2. So then my My particular solution then is y of t is equal to 12e raised to the 2t minus 27t e raised to the 2t. And that is my solution. For my next example here, my characteristic polynomial is 16r squared minus 40r plus 25, and this will equal 0. Now this looks like I might have 4r minus 5, the quantity squared. I'm just going to check this. 4 times 5 is 20, multiplied by 2 is the middle term. Oh, it is. Look at that. This thing equals 0. So I know I have y of t is going to be equal to, it's going to be similar to the one I just did. It's going to be c sub 1 e raised to the 5 over 4t plus c sub 2 e raised to, or don't forget the t, e raised to the 5 over 4t. And I'm just going to give you the solution to this particular initial value. That's the word I wanted to use, initial value. When you get done, and of course we can do this in class, I end up with y sub t is equal to 3e raised to the 5 fourths t minus 6t e raised to the 5 fourths t. Take a look at this next example. Let's take a look at our next example here. So my characteristic polynomial is r squared minus 4r plus 9 is equal to 0. Now this is one I can't factor off the top of my head, so I'm going to throw this in the quadratic. R is equal to 4 plus or minus the square root of negative 4 squared minus 4 multiplied by 9 multiplied by 1 all over 2. So this gives me 4 plus or minus the square root of, well, I get 16 minus 36 over 2. Well, we can see that I end up with a discriminant that's less than 0. So I end up with 4 plus or minus, this gives me negative 20. Negative 20 is 2 root 5i divided by 2, which gives me 2 plus or minus the square root of 5i. Now if I go look at my chart, my general solution then is y of t is equal to c sub 1 e raised to the alpha, the real part, the 2, t, and then it's going to be the cosine of the complex part, which is the square root of 5, t, plus c sub 2 e raised to the real part, which is 2t, the 2 part, not the t, and then the sine of the complex part, which was the square root of 5 multiplied by t. And then, once again, I'm going to use this initial value, and I'm going to find my c1 and c2. I end up finding c sub 2 is going to be negative 8 over the square root of 5, and my c sub 1 is going to be equal to, in this case, it ends up being 0. So my general, or my particular solution, not my general, this is my general solution. My particular solution with that initial value is going to be equal to negative 8 over the square root of 5, e to the 2t, the sine of 5, this 5, square root of 5, I'm just going too fast here, smoking fast here, square root of 5t. And that is the particular solution. This next one is going to be something similar in complex because I know I'm going to have r squared plus 16 is equal to 0. And I already know that my complex numbers is r is going to equal to plus and minus the square root of 16, which is 4i. So 4i. Again, going up to my chart, I have y of t is equal to c sub 1 e to the 0. So that's okay. The cosine of 4t plus c sub 2 e to the 0, the sine of 4t. Well, e to the 0 is just 1, so I get c sub 1 cosine of 4t. and then plus c sub 2, the sine of 4t. Using my initial values like I did before, I'm going to get c sub 1 is going to be equal to negative 10. I'm going to find c sub 2 is going to equal to 3/4. So my particular solution of y of t is going to equal negative 10, the cosine of 4t, plus 3/4, the sine of 4t. So this is a particular solution based on my initial value, and this is the general solution. Now let's talk about what happens when we have equations of order greater than 2. The methods that we just did for linear homogeneous systems with constant coefficients can be extended out to linear ODEs that have powers higher than 2. The characteristic polynomial, it would be what you expect, a sub n r to the n plus a sub n minus 1 all the way down to a sub n r plus a naught. For each real root r bar such that r minus r bar of k divides p of r, the solution must contain c sub 1 e raised to the r bar t plus c sub 2 t e raised to the r bar t all the way down to c sub k t to the k minus 1 e raised to the rt. So in other words, if I would have had one in which the multiplicity on that root was 3, then I would need c sub 1 e to the rt, c sub 2 t e to the rt, plus c sub 3 t squared e to the rt. And k is the multiplicity. Similarly, when we have complex solutions where I have alpha plus bi, beta I, the largest positive integer j, such as an irreducible quadratic form, is in this form. And we end up with this lovely equation going out when we have multiplicities higher than 1. So let's go ahead and take a look at an example here. My characteristic polynomial is r to the third minus 5r squared minus 22r plus 56 is equal to 0. Now you would go back to your pre-calculus 1 solving of polynomials or finding the roots of polynomials. Crack open that pre-calculus 1 book, chapter 3 if you're using OpenStax. I am just going to tell you what this is going to factor into. R plus 4, r minus 2, and r minus 7 is equal to 0. That tells me my r sub 1 is equal to negative 4, my r sub 2 is equal to 2, and my r sub 3 is equal to 7. So my general solution y of t will be c sub 1 e raised to the negative 4t. I like to go in ascending order, but there's no real reason. I just like to do that. C sub 2 e raised to the 2t, and then plus c sub 3 e raised to the 7t. Now, because of the fact that I have 3 unknowns, I need 3 initial values. Here's my first one, here's my second one, and here's my third one, so that I can find all of my unknowns, which is C1, C2, C3. I need 3 equations to find 3 unknowns. And I'm going to do it just like I did before. I'm going to do my first, second, and my first derivative, my second derivative, and then my initial condition. By doing that, I get c sub 1 is equal to 14 over 33. I'm going to get c sub 2 to be 13 over 15, and c sub 3 to be negative 16 over 55. So my particular solution is y of t is going to be equal to 14 over 33 e raised to the negative 4t plus 13 over 15 e raised to the 2t minus 16 over 55 e raised to the 7t. This is my particular solution, and here is my general solution. Let's take a look at one more example. My characteristic polynomial is 2r to the 4th plus 11r to the 3rd plus 18r plus 4r minus 8 is equal to 0. And again, you're going to solve this using your pre-calculus 2 skills and solving by factoring. So 2r minus 1, and then I end up with r plus 2 raised to the 3rd power is equal to 0. So I end up with an r of being 1/2, and I end up with an r being a 3 with a r being a 2. r being a 2 with a multiplicity of 3. And this should be a negative 2. So my general solution then is y of t is equal to c sub 1 e raised to the 1/2 t. This takes care of this one. And then it's going to be plus c sub 2 e raised to the negative 2t. That's my first part of the multiplicity. Plus c sub 2 t e raised to the negative 2t. And then c sub 3, oh, that should be 3. This should be 4. T squared e raised to the negative 2t. Now, I don't have any initial values on this one, so I'm not going to solve that. And if I did, I would need y of something. I'd need y prime of something. I would need y double prime of something. And then I would need the third derivative to be able to solve this, because I have 4 unknowns, C1 through C4, 4 unknowns, and I would need to have those initial values to be able to solve for the particular solution. And that's it for this video.